In this lecture, we are going to apply everything we learned about ARIMA and apply that to stock prices. So this goes back to the fundamental question we asked at the beginning of this section. If we make use of time series analysis, can we predict stock prices? After all, stock prices are a time series, just like airline passengers, just like sales data, and so forth. I think by the end of this section, we've come to learn a few basic facts. Firstly, that ARIMA is a pretty well accepted staple of time series forecasting. Secondly, is that a more modern approach to finding the best ARIMA orders would be to use auto ARIMA rather than trying to pick the orders manually. So this lecture is all about taking everything that we learned and applying that to stock prices. As a side note, I want to mention that this lecture contains no new code which you haven't seen before. So if you feel like exercising what you've learned, you already know what we're going to do. If you want to try to do it all on your own, that would be highly encouraged. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As always, you can check the lectures, how to code by yourself, and how to practice for a more in-depth discussion. If there's anything in this lecture you didn't understand, or you think I missed a step, or didn't explain why we were doing something, please use the Q&A to inquire. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Okay, so let's start by downloading the S&P 500 CSV. Next, let's install PMD ARIMA. Unfortunately, because this library doesn't come with Google Colab, you're going to need to install it manually each time. Next, we're going to import PMD ARIMA, as well as pandas, numpy, and matplotlib. Next, we're going to use pd.readcsv to load in our data as a data frame. Next, we're going to check df.head to remind ourselves what the data looks like. Next, we're going to filter out Google's close prices and assign this to a variable named goog. Note that you also have the option of fitting the log prices instead. For this lecture, we're going to work with the non-logs prices, but you're encouraged to try both on your own. Next, we're going to plot Google's close prices so that we know what auto ARIMA is trying to model. Next, we're going to split our data into train and test sets. We'll use 30 days as the forecast horizon. Next, let's call the function AutoARIMA. Note that we pass in seasonal equals false, since if we pass in seasonal equals true, then we have to pass in the seasonal period, and of course it's not clear what that is. Okay, so let's run this. Next, let's run a model summary. Okay, so we see that the best model found is an ARIMA 310. So does that make sense? The differencing order makes a lot of sense because, as you've seen, returns are pretty stationary. Although the first difference of the raw price is not exactly the return, we can imagine that they are related. To be sure, you might want to plot the first difference and check it yourself. The next thing we see is that the autoregressive component has order 3. That kind of makes sense. It says that the last 3 days of data might be useful in predicting the next return. Okay, so let's look at model.getParams. This provides some interesting information about the model, but not much we didn't already know. The important part of this is that it gives us a nice way to retrieve the order of the model. As you recall, we need to know this, since it affects which days we can make predictions for. For example, if d is equal to 1, then we can't make a prediction on day 1, because differencing always makes the first row an NA value. Okay, so next, we're going to write a function called plot result. This function is very similar to the ones we wrote for the previous scripts. Basically, the point is to plot the data itself, the fitted values for the in-sample data, the forecast for the out-of-sample data, and the confidence bounds. So as input into this function, we take in a trained model, the full data, the trained data, and the test data. The full data is just the data before we split the data into train and test. The first thing we do in this function is to make use of the getParams function we just looked at. This is a dictionary, so first we look at the key order, which gives us the order of the fitted ARIMA. Next, we grab the second component, which gives us back the differencing order D. Next, we call model.predictInSample to get the train predictions. Note that the starting value is D. Next, we call model.predict to get the out-of-sample predictions, along with the confidence bounds. Next, we call our plotting functions. First, we plot the full data. This will be given the label data. Next, we plot the train predictions. This will be given the label fitted. Next, we plot the test predictions. This will be given the label forecast. Next, we call the function fillBetween to draw the confidence bounds. Lastly, we call ax.legend to show the legend. So let's run this. And let's test out our plot result function. So as you can see, the fitted model looks pretty good. Of course, you shouldn't trust a plot like this because it's very small. Unfortunately, it's too small to see whether or not our forecast is good, which is the part we actually care about. So next we're going to write a function called plotTest. The point of this function is only to plot the test period. By seeing it up close, we'll get a better idea of how well our model actually performs. So in this function, we only take in two arguments, a fitted model and the test data frame. Inside the function, we call model.predict to get the predictions and the confidence bounds. Next, we plot the true test data along with the forecast and then the confidence bounds. Actually, this is the same code from earlier, so hopefully you're comfortable with it by now. Next, we test out our new function, plotTest. So what do we see? Well, we see that our forecast is not actually that good. Remember, this is over 30 trading days. One nice thing about this is that it does seem to capture the average quite well. In addition, the true price always seems to stay within the confidence bounds for the most part. Of course, it's worth asking whether a model like this could actually predict what will happen over the next 30 trading days. You know, if Elon Musk goes on Twitter and starts making crazy tweets, I don't think models like this will be able to predict that. Okay, so as you know, one important question we have to ask at this point is, do these models perform better than the naive forecast? Is using these models worth it? So let's define the RMSE function, which you've seen before. Next, let's print out the RMSE for our ARIMA model and for the naive forecast. Note that for the naive forecast, the train prediction can simply be a single value, which is the final value of the train series. This is because series and NumPy arrays broadcast during subtraction, so you can subtract a scalar from an array or vice versa. Alright, so what do we see? Well, we see that although we've done a lot of hard work to train this model, it is in fact the naive forecast that wins. Okay, so next, we're going to do the same thing for Apple stocks. Okay, so note that for Apple, there was a big dip in the price over the last period. It's worth asking yourself, is such a drastic event predictable by an ARIMA model? Remember that these models tend to follow patterns. If there's a trend, it follows the trend. If there's seasonality, it follows the seasonality. But I think intuition, it tells us that models like these do not predict anomalous events. For example, a stock like this rising upwards very quickly and then dropping off all of a sudden. That's not really a pattern, that's more like the opposite of a pattern. Okay, so next, we're going to split our data into train and test. Next, we're going to call auto ARIMA. Again, note that seasonal is false. So let's run this. Okay, so here's the model summary. Again, the fact that the differencing order is 1 is not surprising. What is kind of surprising is that this model is very different from the previous model. Here we have p equals 2 and q equals 2. Earlier we had p equals 3 and q equals 0. Next, we're going to call our function plot result. So as you can see, even with this tiny plot, it's obvious that the true data goes way outside the confidence bounds. However, I think this makes sense in terms of the model we're using. The model seems to just want to carry on the existing trend. Philosophically, I think that's what most models would do. In the context of pattern recognition and machine learning, that makes total sense. Okay, so next, let's call the function plot test so we can see the forecast period close up. Alright, and we see that in fact, the prediction is pretty far off. However, note that in the short term, the prediction is not that bad. Over the first few days, the true values stay within the confidence bounds for the most part. Now, of course, we still have to check the root mean squared error against the naive forecast. Again, the naive forecast performs better than the ARIMA. Next, we're going to do the same exercise, but for the IBM stock prices. Again, let's start by plotting the data. Next, let's split the data into train and test. Next, let's call auto ARIMA. Next, let's check model summary. Okay, so what do we see? In fact, for IBM, the best fitting model is a random walk. What does this mean? It means that IBM stock returns are completely unpredictable given lagged values or lagged errors. Next, let's call plot result. Okay, so nothing out of the ordinary. It does look like the confidence bounds enclose the true values in the forecast. Next, let's call plot test. Again, we see that the confidence bounds enclose the true values. In fact, this prediction doesn't look that bad. The actual price crosses through the prediction line multiple times. So what happens when we check the root mean squared error against the naive forecast? Well, we see that they are the same. Since this is a random walk model with no drift, the forecast is just the last known value, and it's the same as the naive forecast. Okay, so next, let's try Starbucks. Again, let's start by looking at the plot. Next, let's split the data into train and test. Next, let's call auto ARIMA. Next, let's check the model summary. Okay, so here is another random walk, ARIMA 010. Note, however, that this is a random walk with drift, since the model fits with a non-zero intercept term. Next, let's check plot result. Okay, so it's a bit hard to see what's going on during the forecast. Next, let's check plot test. Alright, so this doesn't look too bad. It's decently accurate for the first few values, and then it overestimates the price when the price drops. Although most of the time, the price does stay within the confidence bounds. So the lesson is, don't ignore the negative side of your confidence bounds. Those values are perfectly achievable, and they result in a loss of money. So what happens when we check the root mean squared error? Well, although we detected that this was a random walk with a non-zero drift, it turns out that assuming a random walk with zero drift would have been better. The naive forecast wins again.